Howdy class, should be Wednesday's lecture. This is lecture number 10, and the last couple of lectures we've been talking about semiconductors, and I know you understand fully by now that they are integral and the principal component in computers and microcontrollers and electronics in general. We're going to get into some semiconductor or transistor type devices today that are extremely important for measurement and control. So with that said, let me switch over to the video or the screen here, and we'll get our lecture started. So this is operational amplifiers, fundamentals. So you'll remember that at, I guess, about the fourth lecture of the semester, I said there are 5 fundamental things that you need to know in solving circuit problems. I'm going to give you just a minute to try to remember what they are. So now I'm going to go ahead and confirm your thoughts. Number 1 is Ohm's law. Everybody should know that like the back of your hand. Second is Kirchhoff's laws, KVL, KCL. You should know those almost as well and be able to use them in solving circuit analysis problems. Remember that you can define loops and nodes in circuits and add up voltages in loops and add up currents at nodes and make calculations about circuits that way. Third, circuit equivalents, Thevenin and Norton, and we covered them cursorily. Again, those are a little more difficult conceptually for those of you who haven't been in electrical engineering for 3 years or so. We kind of just touch on them so you know what they are and how they relate to circuit analysis in general and what the importance of them is. The fourth thing I said was Euler's formula, and we covered that in about the last week and a half or so. Pretty simple in terms of taking AC signals and adding them together when they're of like frequency. The last thing is the 2 golden rules of op amps. So let's talk about that concept today, operational amplifiers. Op amps are solid-state integrated circuits that use external feedback to control their functions. And they are one of the most versatile electronic devices, and that's why we will spend time on them and why the 2 golden rules of op amps are so important. In terms of operating characteristics, you can see that they have the schematic at the right. You've got 2 inputs and 1 output, and these are your supply voltages, your positive supply voltage, your negative supply voltage. And it's common practice to omit the power supply connections and diagrams, so you typically, those dotted lines there, you won't see them. You'll just see the 2 inputs and the 1 output. It's also important that you've always got your minus and plus signs denoted so you know which is your inverting and which is your non-inverting input. So the voltage difference between the inverting and non-inverting terminals defines the basic operating characteristics. Without external devices, an op amp will operate in open loop mode. That is referring to a theoretical op amp, okay? And we talk about a lot of things in theory that don't work exactly that way in practice, but this is a theoretical op amp. It has infinite open loop gain. Okay, now would that be good? Yeah, I would say yes. That would mean that we can perfectly represent our input signal. Infinite input resistance, yes, very good. 0 output resistance, yes, very good. All those things are great for an ideal open loop op amp, and it will follow the operating curve at the right. So when the input of the non-inverting terminal, and think just a moment, remember what the diagram looked like. That's the terminal going in by the minus sign, sorry, with the plus sign. When the input of the non-inverting terminal is less than that of the inverting terminal, the op amp output is negative saturation voltage. So there is a maximum voltage that op amp can generate. That's called its saturation voltage. And in this case, it'll be to the negative. When the input of the non-inverting terminal, again, the plus sign terminal, is greater than that of the inverting terminal, the op-amp output is positive saturation voltage. And as it crosses over, it goes perfectly from negative saturation voltage to positive saturation voltage. Again, this is for an ideal op-amp. Real-world op-amps are not quite that good, but they're still pretty good. Now, one class of ICs, which is a short term for integrated chips, is called comparators. And they operate like open-loop op-amps. And they're used in logic circuits to compare two voltages and provide one of two possible outputs. So think just for a moment, going back to the early lectures in this semester about measurement control. If you think about your process diagram, your block diagram, you've got a point where you've got an error detector, if you will, that has a set point and it has an input measurement. And it will compare the input measurement to the set point and give an output to the controller to make a decision on. Okay, comparators, these integrated chips called comparators, do this. Okay, they compare two voltages and provide one of two possible outputs, a 0 or a 1, or a false or true. And we'll talk about this a little bit more later when we get into logic. But I just wanted to introduce that now because they do work in similar fashion to open-loop op-amps. Op-amps are very useful when the output of the op-amp is connected to the inverting input of the op-amp. So take a look at this. You've got two inputs, inverting, non-inverting. So you've got a voltage coming into the non-inverting, and the output of the op-amp is connected by wire back to the inverting input. This causes the output right here to provide negative feedback to the input. Okay, so the op-amp's able to say, okay, this is what I've got coming in, and now I also know what I've got going out, so I can adjust my operation based on that feedback. This circuit in that configuration is called a voltage follower. Okay, I'm going to show you several configurations of op-amps. You need to memorize them. This one is called a voltage follower. Evaluate it with the last of the 5 things that you need to know for circuit analysis. All right, I just told you what those were earlier. Number 5 is the 2 golden rules of op-amps. So now we're going to tell what those are. 1, the output always changes to make voltages at both input terminals equal. Okay, so let's go back and look at that again. This op-amp will produce an output here that will try to force these voltages to be the same, such that there's no difference between voltage at the non-inverting and the inverting terminals. Okay, I'm going to read that one more time. Output always changes to make the voltages at both input terminals equal. Golden rule number 1. Golden rule number 2. No current enters the op-amp. It has infinite impedance at the input. Okay, so let's go back and look at this again. Either at this input terminal, the inverting input terminal, or the non-inverting input terminal, there will be no current coming into the op-amp there. Okay, so let's think about a question here. If we've got voltage here and we've probably got some current going out here, but there's no current coming in here, where's that current coming from? All right, let's go back and look at our earlier diagram. One more, I think. Okay. You have positive and negative voltage supplies here that provide the electrical power for you to get a current output in the output of your op-amp. That output is controlled by your inputs. And if you'll think back to our discussion about transistors and BJTs and FETs, you remember that you're typically controlling the flow of current, for example, from the collector to the emitter by changing the voltage on the base. So here what you're doing is you're changing the output here by what is occurring in the voltages at these inputs. And the current that's being provided to this output is coming from the voltage supply, which we don't show in the diagrams. All right, let's try to get back to where we were real quick. Golden rule number 2, no current enters the op-amp at either terminal. Okay, so because of golden rule number 1 and what was number 1, output always changes to make the voltages at both input terminals equal. Because of rule 1, the output will match the input on the non-inverting terminal. Vout is equal to Vin. Because of rule 2, no current flows at either input terminal. So we could put almost any circuit ahead of the voltage follower without causing problems. Remember that input impedance of electrical devices needs to be higher than output impedance of the device feeding into it, right? Otherwise, we don't get an accurate representation of our input signal. The infinite input impedance of an op-amp satisfies this need. As with other electrical components, several things must be specified when selecting op-amps. So let's look at some of those. This is a very typical op-amp here. It's made by Fairchild Semiconductor, KA741. Similar type is available from Texas Instruments, model number UA741, National Semiconductor, so on and so forth. This is what it looks like. It's got 4 pins on each side. It is a general purpose. Whoops, I jumped one too many screens. Up, I jumped back up. So let's go back down here. It's a general purpose op-amp intended for a wide range of analog applications. Okay, so you need an op-amp. This is a good op-amp. Has high gain, which is good because basically you're wanting to produce a larger signal with a smaller control signal. It also has a wide range of operating voltages that provide superior performance in several applications as an integrator, as a summing amplifier, and for general feedback. It has short circuit protection. It has excellent temperature stability. It has internal frequency compensation. High input voltage range, which is very nice because that makes it useful for a wide variety of applications. And it has a null offset, and we will, I think, talk about what that means later, what the null offset means later. So let's talk about some of these features of this op-amp. Note that the absolute maximum ratings are given here, and this is at an ambient temperature of 25 degrees C. So basically room temperature is the temperature at which all these things are true. Supply voltage plus or minus 18 volts. That's the range over which the supply voltage can operate. The differential input voltage, 30 volts. The input voltage plus minus 15. Okay, the difference between those two is 30. The output short circuit duration is indefinite. So you can have an unlimited short circuit output on this. That may not be meaningful to you at this point, but hopefully as we go along, some of these things will become more meaningful. Power dissipation, 500 milliwatts. Operating temperature for the K741 is 0 to 70 degrees C. 70 degrees C is pretty hot. Off the top of my head, I think that's on the order of, 150 degrees, something like that, Fahrenheit. Note that the K741I, this is basically mil spec or military specification, can operate at minus 40 Celsius up to 85 Celsius. So it's basically a ruggedized version of the K741. Storage temperature, very wide range without damaging it, minus 65 to 150 C. All right, supply voltage. That's the maximum voltage, positive and negative, that can be used safely to power the op-amp. Anybody remember what that was from the last slide? 18 volts. The differential input voltage on the last slide was 30 volts. That is the maximum voltage that can be applied across the non-inverting and inverting inputs. So you could have a lead coming to each one, and the voltage between those two leads would be 30 volts. That's the max it can accept. The input voltage, meaning compared to ground, maximum input voltage that can be simultaneously applied between both inputs and ground, I believe was 15. That's also referred to as the common mode voltage. In general, the maximum voltage is equal to the supply voltage. Okay, in this case, it was a little bit less. Our maximum voltage was 15, our supply voltage was 18. But they're pretty similar. Output short circuit duration, we talked about that. That was indefinite for this particular op-amp. That is the amount of time that the output voltage can be short-circuited to either supply voltage. Okay, so that means that you can hook feedback directly in, that voltage follower. You can have the output hooked directly back into the input indefinitely, no problem. Power dissipation, 500 milliwatts at 80 degrees C. That's the maximum power the op-amp is able to dissipate at a specified ambient temperature without getting too hot. The operating temperature range, that's the ambient temperature range for which the op-amp operates within specs. It'll continue to operate if you get it outside of that range, but it'll start messing up. And that's why, as I mentioned in class the other day, these days in modern computers, you have temperature sensors on them that tend to give warnings when your CPU or your central processing unit in your computer is running too hot, because you begin to have errors in the function of the device. The ambient temperature was, I can't remember exactly what it was, but I'm sure you probably remember better than I do. But you also remember that the military grade version had a much wider temperature range than the commercial version. Storage temperature range just is you can store the chip at any one of those temperatures without damage. And as I showed you before, it's an 8-pin chip, okay? And the pins are numbered as follows. 1 at the upper left, and you'll notice, and I'll go back and I'll show you a picture in just a minute if I can get my cursor working here. You've got a little indention in one corner of the op-amp, and that helps you to know which pin is which. The number 1 pin is always next to the indention, okay? And then the numbering of the pins goes down 2, 3, 4, and then directly across to 5, and then back up 6, 7, 8. And you can see this diagram as to which pins are the inverting and non-inverting inputs and which is the output. So 2, 3, and 6 are the main ones that we're going to be considering when we look at a schematic of an op-amp. But you've also got this null offset, an offset null here. You've got common mode voltage here, another input voltage here, or supply voltage here. And let's see what some of these are. Pin 1 and pin 5 are offset nulls. That is, if the exact same voltage were applied to inputs of an ideal op-amp, the output voltage would be 0. Okay, in the real world, though, there is some small input voltage for this condition. Sorry, some small output voltage for this condition. So let's say that we've got 2 perfect power supplies, and we're putting 5 volts here and 5 volts here. An ideal op-amp would produce an output here of 0 volts. But what we're saying here is that in the real world, some small output voltage will exist for this condition. That's called the offset voltage. But we can cause that to be 0 and basically calibrate our op-amp by application of a voltage of opposite polarity to the offset pins. So we've got offset pins 1 and 5. We can put this voltage, this output voltage, to 0 that small output voltage out. So that's what those are for. Pin 2 is the inverting input. All input signals at this pin will be inverted at pin 6. So if it comes in here as a positive 5 volts and that's the only thing coming out, it'll be a negative 5 volts over here. It's important to ensure that pins 2 and 3 get the correct input signals. Otherwise, the op-amp cannot do its work. Pin 3 is the non-inverting input. All input signals at this pin are processed normally without inversion. Pin 4 is VEE, that is the negative supply voltage terminal. And again, we would be seeing this as a dotted line input on that earlier diagram right here. Supply voltage operating range is minus 4.5 volts minimum to minus 18 volts maximum. Okay, so at this one, this is the negative supply voltage terminal. We have to have between minus 4.5 volts up to minus 18 volts. 741 is specified for operation between 5 and 15. So really, if you're up at the 18 volt or down below the 5 volt range, you're sort of outside of specs. Devices operate. The device operates consistently over this range of voltages without change in its timing period. Okay, now bear in mind, don't confuse the negative power supply voltage with the ground. Pin 6 is the output. The output voltage from the op amp, we already talked about that. Pin 7 is the positive supply voltage, and it's rated almost exactly the same but opposite of the negative supply voltage, from positive 4.5 volts up to 18, but again the operating specs are between 5 and 15 volts. And the device operates consistently over this range of voltages without changing the timing period. So that's why they spec it out from 5 to 15. The most significant operational difference is output drive capability, which increases for current and voltage as supply voltage is increased. Okay, let's say that again. The most significant operational difference is output drive capability, which increases, meaning you can put more power out as supply voltage is increased. Okay. Sensitivity of the time interval to the supply voltage change is low, typically 0.1% per volt. Pin 8, NC, stands for not connected. So you've got an 8-pin configuration. One pin doesn't really do anything. It's just there to make a standard 8-pin package. With that, I'm going to go back to the camera. And so that's a little bit about op amps. You really need to focus on the 2 golden rules of op amps, what they mean. You're going to have some homework that's going to require to use those 2 rules in some circuit analysis. So please think through that and get familiar with it. And that's all I have for today.